Yeah, what's up? It's Mr. Mangle. So the worksheet that you should have is the Introduction to the Law of Sines and the Law of Cosines worksheet. Uh, this is what it looks like. It talks about my little brother and me. Cool. So we're going to start out with a little bit of review of geometry. And even if you haven't had geometry, it's alright. We've talked about SOHCAHTOA, and that is how we're going to solve the first problem. So the first problem reads, and this should be just a review of old stuff that we've already done. Mr. M and his little brother are flying a kite at the park. Anil, I have 3 brothers and that's my youngest brother. A cute little boy is holding one end of a kite string so that it is 4 feet above the ground. So we have Anil, Mr. M, kite string, so it's 4 feet above the ground. The other end of the kite string is attached to the tail of the kite, which is blowing in a breeze. The angle of elevation from Anil to the kite is 14 degrees. So the angle of elevation, elevation means going up, right? Is 14 degrees. Mr. M is standing directly below the kite and is standing exactly 68 feet away. Mr. M, directly below the kite, exactly 68 feet away from Anil. So based on all the information, how high above the ground is the kite? Well, the first thing you want to do is you want to form a diagram. You want to draw it out. After you draw it out, you're going to want to figure out a way that you can solve this problem using the trigonometric ratios that you know, SOHCAHTOA. Cool. So let's see what we can do. Let's see what we can draw. So let's say we have a little brother right here holding a kite string. Here's the kite. Little kite's tail blowing in the wind. Okay. Here's Mr. M standing directly below the kite. Alright. That's our diagram of our triangle. What else do we know? We know that the angle of elevation from which the kite is being flown is 14 degrees. So this is 14 degrees. What else do we know? We know that Mr. Mangle is standing directly below the kite and he's standing exactly 68 feet away. So that tells us how far Mr. Mangle is from Anil, which is 68 feet. And the question, and we also know that he's holding the string 4 feet above the ground. So the height above the ground that he's holding the string is 4 feet. So 4 feet is the height above the ground at which he's holding the string. So it's the question that we're trying to answer is how high above the ground is the kite? How high above the ground is the kite? That's the question that we're trying to answer. So if I'm going to call that, let's call that H. H for height, how high above the ground. Well, when I look at my diagram, I have a triangle. Wow, I have a triangle. It's a 90-degree triangle because I'm standing directly underneath the kite. So I know that angle that it makes has to be 90 degrees because anything that's directly beneath and has an intersection is that it's always at 90 degrees. So I have a 90-degree triangle, I have a degree measure, and I have two of the sides of the triangle. Do I know any trigonometric ratio that involves the opposite and the adjacent? Yeah, tangent. So the tangent of theta, I know, is equal to opposite over adjacent. So that will help me find my height. So the tangent of my angle, let's see, so our angle degree we said was 14 degrees. is equal to the opposite, which is h, divided by my adjacent, which is 68 feet. Can I solve for my height? I think so. We'll do it. So to solve for your height, all you got to do is multiply by 68. When you do that, you're going to end up with the height equal to 16.954. So the height is equal to 16.954 feet. Is this how high above the ground the kite is? No, that's actually the height of the kite from where Anil's string is. So how high is it above the ground? Well, this height plus the 4 feet that it's already above the ground. So 16.954 plus 4 feet gives us an answer of 20.954 feet above the ground. That last part is very, very, very important. Make sure you include your units. And that's how we would solve this problem. This problem should have been very, very simple. If you feel a little uncomfortable with this problem, or if you feel that you need more practice, definitely ask me for more support. Ask me for more problems so you can practice this, because these problems should be very, very easy. They're definitely going to be on the common assessment and your upcoming test on Monday. These should be baby problems compared to what we're going to be doing. So in geometry and physics, we've used our knowledge of right triangle trigonometry to find the measures of angles and sides in right triangles. So everything that we've learned about trigonometry, we've used everything we know to find the angles and the sides by using SOHCAHTOA, by using by using all of the little acronyms, by using everything that we know from right triangle trigonometry, we can figure out angles and we can figure out sides. However, we don't live in magic land. I mean, this isn't a white picket fence world all the time. I mean, there are times whenever you do see triangles that do not have right angles, right? Like, they occur all the time. So that's what we're going to be learning today. We're going to be using certain laws. We're going to be using certain laws and rules. They're called the law of cosines and the law of sines in order to determine what angles or sine measurements would be if a triangle does not have a 90-degree angle. So when a triangle doesn't have a 90-degree angle, we know that we can use the law of cosine and the law of sines in order to figure out what those angles or the sides may be. That is our ultimate goal, to be able to solve for the sides or the angles. That's what we've been doing whenever we've been using right triangle trigonometry. So let's get to it. So the law of sines and the law of cosines can be used. Okay, so this is just a description of the real world. So in the real world, we rarely have this much information, and even less often do we get perfect right triangles. So we don't always have all the information that we're looking for. We don't always have everything that we just saw in the last problem. We even have less information. So often there are physical obstacles which prevent us from finding these measures directly. In cases like these, we need more sophisticated methods. The law of sines and the law of cosines can be used for any triangle provided that you have the needed information. So for right now, we're not going to worry about the proofs of these trig laws. We're just going to use them. So I'm not going to make you prove these trig laws right now. We're just going to use them. So let's start with the most generic triangle possible. We know nothing about the sides or the angles. So we know nothing about the sides or the angles of the most generic triangle. But what I want you to see is that the big letters in these triangles, do we see a 90-degree angle? No. But we should see that there are letters. The big letters correspond to the angles. So big C, big B, big A, those are corresponding to the angles. Directly across from those angles are the corresponding side measurements. So little c is across from the angle C. Little b is across from angle B. Little a is across from big angle A. Okay? So, there are some very, 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 very important geometry facts that you have to hold on to. You have to keep these in mind. So all angles in a triangle must add up to 180 degrees. So all angles in a triangle must add up to 180 degrees. So if I add up big A plus big B plus big C, it has to equal 180 degrees. This is a must. They have to add up to 180 degrees. The smallest angle is always across from the smallest side. So the smallest angle in this triangle, let's just say if C was the smallest angle, it would have to be across from the smallest side. So that makes sense because if you have a 15-degree angle, the side opposite of 15 degrees has to be smaller than, say, a 30-degree angle. Or let's just say 30-degree angle, the side opposite has to be a lot smaller than a 60-degree angle. 60-degree, opposite of 60 degrees, you know, is square root of 3 over 2. Opposite of 30 degrees is 1/2. Square root of 3 is bigger than 1/2. So that makes sense. So the smallest angle is always across from the smallest side. Same for the longest side and the middle side. The third thing, when we're naming the sides and the angles, be sure to place the side across from the angle with the same exact letter. So with the angle C, I put baby C, exactly opposite of that same exact letter. All right. Whoop, whoop. All right, cool. So, the law of sines. So, we're going to use the law of sines and the law of cosines in very, very, very specific situations. So, sometimes I'm going to give you only one side and a couple of angles. Or I'm going to give you all the sides. Or I'm going to give you a couple of angles and a side. But we're not going to be, in most of these problems, whenever we're using the law of sine or the law of cosines, we're going to have triangles that do not have right angles. Or they don't have angles that are 90 degrees for the most part. So, the law of sines. So we're going to use the law of sines. When do you use it? It's to be used when you know a side and when you know the opposite angle. So when you know one of the sides, and for that same side, when you know the opposite angle to that side, that is when you would use the law of sines. Well, what is the law of sines, you're probably asking? Like, what the heck is the law of sines? Well, the law of sines says that the sine of angle A divided by the side little a has to equal the sine of angle B divided by the side little b, which is equal to the sine of angle C divided by little c. That is the law of sines. We're going to put it into practice in a couple minutes. So the law of cosines. You use the law of cosines in two situations. You can use them in two situations. The video is about to end, so turn to the next video.